Okay, good evening, everybody. It's my great pleasure to welcome you back for Donna Strickland's third Einstein lecture. And for those who were not here before, I should say that you're most welcome by the Faculty of Science and the Albert Einstein Center for Fundamental Physics at Bern University. But I also welcome you in the name of the Albert Einstein Society, which has been our co-organizer since 2009 when we started this lecture series. So we have the great pleasure to have Donna Strickland here from Waterloo University in Canada. And she was born in Canada, in Ontario, studied at McMaster University, then got her PhD from Rochester University and got involved in laser physics and developed the technique of chirped pulse amplification. So you take laser pulses and you intensify them without damaging the laser material. And that had enormous applications in basic science, but also, as we learned yesterday, medical applications. And as you already know, she won the Nobel Prize for that. As the third woman ever to win the Physics Nobel Prize after Marie Curie and Maria Goeppert-Mayer. I think we have, if you were here before, experienced Donna as a really enthusiastic, very forward-going and good-humored person who really wants to take her head and put it on the laser equipment, turn these knobs, and then, of course, also think about the mathematics that is necessary to actually understand what's going on. So it's really very much engaged in her research, even after becoming a Nobel laureate, and still now also taking that as a opportunity to educate the public, to generate excitement in the young generation, and I think you have already proved that you are very good at that. There is another aspect which I think we'll see today, and that is related to the fact that you are ready to shoulder additional responsibilities. For example, Donna Strickland was the president of Optica, which is the American Optics Society. Now this Optica has combined with the American Geophysical Society, and they initiated this GEMM initiative, which engages itself in global environmental measurements and monitoring. So the goal is, if I understand correctly, first of all, to bring people together who can work with equipment in the laboratory, build sensors, in order to monitor what's going on with the climate, and really also talk to the people who need to make these measurements in different places. But not only that, also bring the policymakers into this business. And I imagine that it can be quite helpful to have a Nobel Prize winner to motivate politicians, right? I mean, physicists are kind of generally interested already in the physics, but to bring scientists and policymakers together, I'm sure you're one of a few people who can actually do this. And as we very much appreciate at Bern University, climate is definitely, and not only for us here, a big subject also in research. I just see Thomas Stocker and Hubertus Fischer here. Climate research plays a very important role at Bern University, so I think we would like to see this interdisciplinary character of your work in this third lecture.
Okay, thank you. That's not showing up there anyway, so, okay, that's weird. Sorry, I'm seeing something on my screen, but it's not up there. So thank you very much. I've enjoyed giving these 3 talks. The last 2 were about the research I do, and this, as I've already said, is much more about my public policy endeavors with Optica, and somewhat a little bit now with the Canadian Association of Physicists. So it is about bringing people together. So this one, because some people have said they had some trouble following my physics, this one, because I am going to tell you a little bit about optics, but so little. Most of this is not very scientific. Okay. So what are we talking about? Well, I actually should say, why did Optica even get interested in this? And the AGU came in after Optica. And so to be totally transparent, it really started because the year I was president of Optica, there was a National Academy of Sciences report came out, and the big optics organizations wanted to make use of it because it was about how important optics was. And the first 10 years before when they had done it, the Europeans really used that NAS report and came up with Photonics 21 for Europe. And yet the United States didn't make use of their own report. So this time they really thought, we're going to make use of this report. And we're going to get organized, and we're going to start an organization. And they called it the National Photonics Initiative. But then they came to me and they said, Donna, you can't be the Optica rep on it. I said, I get it. It's not my nation. That's fine. I said, but just remember that a lot of us, 60% of OSA's members, we're not American, right? So I said, you got to also, make sure that we get out there and explain to all governments how important optics is. And then in 2015, it was the Paris Accord, where Tom Baer, who had started the NPI, said, that's the one thing that all governments care about. Ironically, not so much the US, but anyway, it was supposed to be for everybody but the US anyway, so it sort of worked. So we decided that this was the public policy that we could go out with and explain the importance of optics to the government, okay? The other thing I will tell you about those of us in optics, we like to think that our science is useful everywhere, okay? So we could have picked a lot of things, but this was the one that we thought would speak to the government. So that's how I got involved. All right, so when we talk about the environment, a lot of people think that what we're talking about is measuring CO2 in the atmosphere. But to understand the climate and have a really accurate climate model, it's going to take so much more than that, because there's so much more to the environment than just the atmosphere. So I'm showing all the spheres here. I think I'm showing all the. I have experts here, so if I don't have all the spheres, you could let me know. But this is the one that we mostly talk about, and I am going to refer back to this picture, so I want you to really think about this picture taken by a Canadian astronaut. Just pointing that out. Okay, so first of all, this is our Earth, which is mostly water, and then some Earth. And this little blue layer here is our atmosphere, and then this is the nothingness of space. Okay, so I'm going to refer back to that nothingness of space in a minute, and I'm going to talk about this beautiful blue sky. Okay, so that's the atmosphere, and this, to a large extent, this is what we think of as warming, because when we say what's the temperature out, it's usually the temperature of the air that we're talking about. But the temperature of the air affects all the other spheres, and the other spheres affect this. And so let's go here. The oceans, this one, and again, I only took the ones that were free to take from the web. So this one is showing the currents, but this has a lot to do then with what the weather is that's showing up on your shores. But also because the air is heating up, so is the ocean. But also there's a whole lot of biosphere inside the oceans, and that's also changing the temperature of the oceans. But the other thing about the oceans that we worry about is, are they rising as the temperature goes up? And the reason we're worrying about that is because of the cryosphere. Now, for reasons that environmental people can probably tell us, Antarctica is not warming up, but as fast, at least. The fastest warming is up in the Arctic, okay? And so this ice is melting, and as it melts, then the ocean is going to rise. So that's affected. The one that we probably have the least to do with, but we do have fracking going on in the geosphere. But nevertheless, when the volcanoes erupt, we all know that it has a huge effect on the weather, so it has to be studied. And finally, we absolutely need the biosphere to live. This is the water we drink and the food we eat. But the biosphere is also the ones that are helping us control the levels of these greenhouse gases. So it's all together. And the one thing I want to point out, especially about the biosphere, is I have had this opportunity to go to this conference where astronauts speak, and almost every single astronaut that has spoken and said that they had this opportunity to look back at the Earth, like this astronaut has, is that they said it really drives home the fact that Earth is our spaceship. And they want to make clear that everybody understands that the Earth is going to keep going around the sun, with or without people on it. The Earth could care less, okay? The Earth could care less that we're here. So when we talk about saving the Earth, we really only mean saving humanity. That's all that we're really worried about, is can we keep the Earth in a place that's really good for us humans? Okay, so this is a whole lot to study. And that's the point of needing a whole lot of measurements. All right, and so then, this is just a great quote that was more than 100 years ago by Lord Kelvin, and it was about electrical units of measurement, but it still applies. So when you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. And so this is where the optics people are going to come in. We're going to try to put numbers to it. It doesn't have to be just optics technology. The AGU will bring in other technologies as well. Okay, but I am here as an optics expert. And so what is optics? The actual real definition of optics is the study of light. And light is the part of the electromagnetic spectrum that we see with our eyes. But I already said that in the very first lecture. It's not even an octave of light. It's not even a factor of 2. All right, and so that kind of is limiting for us poor optics people. And so we've just chosen as a community to take a lot more of it than that. So we would say that we go from the IR through the X-rays, and we'll say all of this is optics now, okay? Some people in X-rays and IR may disagree with us, but we optics people are going to take it all, okay? So we can talk about all of this. Okay, so then why do we think optics is so important and can be used for so many things? It's because when it interacts with matter, it can change in so many ways. And so this video, this was given, I got this slide from Institut National d'Optique. This is a Quebec, I'm pretty sure the nation is Quebec and not Canada. But it's hard to know. But it is in Quebec City, and it is a research institute about optics. So this is showing light through a prism, and I'm sure we all know that when you put in all the colors, they come out and they get separated. But I'm just going to stop. This is going to be one little bit of my optics lesson for you, and talk a little bit about, in physics, we cannot understand all of physics at once. Whether you're a theorist or an experimentalist, you can only look at it in certain regimes. And so we break them down into different limits, and depending on what we're trying to study, the limits can even change. But there's sort of 3 areas of optics, and the limit is the wavelength much smaller than the object it's interacting with, roughly the same size it's interacting with, or the wavelength is much bigger than the object it's interacting with. So if the object, in this case the prism, is much bigger than the wavelengths, then this is known as geometrical optics or ray optics. And then this is what the camera developers use, and there's the law of reflection. Now this one is kind of whoever did this. If it was just a single color, and it was polarized the way they're showing it being polarized, where the light's going up and down this way, one color, if you hit it exactly at an angle known as the Brewster's angle, no light would reflect. But because it's white light, technically they should be showing you another beam coming off this direction, and it would follow the law of reflection that we know. The angle that it bends here is the angle of refraction. And so this and ray optics are well known, and probably you even learned about them in high school, and they go by Snell's laws. So this you can know if the wavelength is much smaller than the object. But it really doesn't explain why the light bends. if you really want to know why the light bends, you have to dig down a little deeper and understand that the ray is perpendicular to the front of the wave, right? And so the wave fronts are going perpendicular to this. And so you have to know then, you have to do wave optics, or it's also called physical optics, when you can look at light being a wave and not a ray. So why is that? Why does it bend? Well, if it's a phase front coming here, before it gets there, it's a phase front. They all travel the same distance because they're all going the same speed. But then this one, as soon as it hits this object, it has to start traveling slower inside. It will make its own radius in a certain amount of time. But this one up here gets to keep going till it hits all the way here. So when this one has gotten all the way here, this one has not gotten to travel that far. It's traveled less. And that's why it actually bends, because the phase front now is this one got all the way here, and all the rest slowed down, so it's doing this. So this had to be understood by digging down a little deeper and look at it on a wavelength dimension. But that doesn't explain why the different colors bend differently. And the reason that the colors bend differently, you have to then go all the way down and look at the interaction of the light with the individual atom, okay? And so it is then, this is the quantum limit, when you finally have to look down there. And so, again, in my first lecture, most of what I was talking about Raman, but I did talk about the index of refraction. And so it really is the fact that it goes up, there's a virtual state, and that virtual state has to do with how close are you to the real states. And if you're closer to the real states, you stay there longer, and that's why blue travels slower and the red travels faster, because it's further from that. But you do have to know the quantum mechanics of the object when you scroll right down. So this one little example of how come light bends and comes out with different colors bending more has to do with the geometrical optics, the wave optics, and the quantum optics. And so it's all there. And so the fact that we have studied all this way of how light and matter interact is why we can now maybe use it in order to study the environment, along with a lot of other things, that we already know how it interacts with this. So it will change, the intensity will change, the light could be absorbed in this object, the light could be reflected from this object, whatever. You could have less power here than you had coming in. The color I've already showed will change. The polarization, I won't talk about so much in this talk. This one is showing linear polarization, that it's going up and staying up. But there is ways to make it all of a sudden, be polarized in a different direction. And the direction of propagation is definitely being shown here. So all these things happen, and so you can just use light to tell you something about the material it's interacting with. So then I'm just going to use a very common and a very simple example. Why is the sky blue, and why are clouds white? So first I want you to remember the picture with the black nothingness of space, so that we can even understand that the answer to both those questions is scattering. It's not the same kind of scattering, but the answer is scattering. And so in that picture of showing the Earth and the black there, the sunlight was over here, and the sunlight going by, if it doesn't hit the Earth and it doesn't hit our sky, it keeps on going, because there's nothing there to scatter it. There's nothing. And so the light just keeps going. And therefore, it can't go into your eye or it can't go into your camera. Just take a picture of the camera, because the light that was going this way has to scatter in order to come to your eye, and if it doesn't come into your eye, you don't see it. And black is the absence of all light. When you see black, it's the absence of all light. All right? But when the light came through and didn't, again, hit the Earth, but came through our atmosphere, then it scattered and it came towards our eye. And so we see it, right? Same thing with the clouds. It came through. If there was clouds in the sky, it hit the cloud and came into our eye. So in both cases, it's scattering. The light was going this way, and now it's going this way. But obviously, it's different, because all the colors of the sun are hitting our sky and the clouds. We only see from violet to red, so it doesn't matter what's happening to the others if you look with your eye, all right? But there's something different about the sky, because all the colors are scattering, but of the colors we see, more blue scatters than the other colors. Not just blue, because if it was just blue, it would look like a nice royal blue, and the sky does not. And if you were trying to paint your house, and you wanted to paint your house sky blue, but you only had royal blue paint, I'm sure you would know that you would just mix it with some white paint, okay? You would mix that royal blue paint with white paint so that what reflects off the walls is white, but also extra blue, okay? And so that's what makes it sky blue. It's white with more blue. So if you can imagine, just a square spectrum of light coming by, it's now tilted like this because there's more blue. This is known as Rayleigh scattering. And you only see Rayleigh scattering if the scatterer is much smaller than the wavelength of the light, okay? So just by looking at this blue sky, we know the sky is made up of objects much smaller than the wavelengths we see, which is about 1/2 micron. And so it's made up of molecules. So I'm going to explain Rayleigh scattering, because I have to do a little bit of physics here. So if you have a molecule, and it's sort of strung out here, so this is going to be my molecule, this part of my arm, and the light's going to come, and we can have it linear polarized this way. It's randomly polarized, but that doesn't matter. It's polarized this way, and it hits this molecule. It will drive the electrons up and down. But you can see that if the molecule is oriented this way, it's much easier to make everything happen along this direction. And so you will drive the electrons back and forth, back and forth. Now, if you have charges separating with the negative charge going one place and the positive charge going the other place, I also showed you that was the way to make an electric field. The electric field would point from the positive charge to the negative charge. The next oscillation, the negative charge is down here, and so you had an electric field here, electric field here, electric field here, electric field here. And a moving electric field is an electromagnetic wave, and it has to go out this direction. It can't actually go this direction. That's the one direction it can't go, and you might wonder why. You have to, if this is the negative charge and this is the positive charge, and a molecule, I've already told you, has to be much less than the 1/2 micron of the wavelength. So it's very tiny. You go a millimeter away from that. Then you see a positive charge making an electric field this way, a negative charge really close by making the opposite sign. And so the electric field out this direction is 0, and out this direction is 0. Every other place you're seeing the electric field do this, and you scatter. Now, the molecules in our sky are here, here, here. They're all directions, and that's why when the light comes here, it scatters in all directions, okay? Why does it scatter blue more than red? Again, it comes back to the quantum levels, or pushing on a swing like I talked about before. The blue is much more resonant, and so it just happens that you cause this reaction a lot more in blue than you do in red. And so it scatters more blue than it scatters red. So then why is our sunsets red? If you want, I'm just going to finish the whole story. Sunsets are red because, again, that layer of sun, while you're watching the sun go down, it's not going through that little distance. Don't ever look at the sun when it's going through a little distance of, because although it's scattering, it's not scattering a lot. But when it's setting, it's scattering through that whole layer. And the blue is being scattered away, and the red is coming at you. Okay, that's why we have these beautiful red sunrises and sunsets. All right, but now the clouds are white. And if you see the clouds being white, I'm not going to explain why they get dark. That's a different story. But the clouds being white tells you that all the colors get scattered towards your eye, but all equally. That's the signature of me scattering, and that tells you that the objects are at least the size of the wavelength. So that we know clouds are made of something that's of objects at least the size of a 1/2 micron. Okay? So we know the sky is made of really tiny things, and the clouds are made of things that are at least on the order of a 1/2 micron. And so just by doing that, just by a simple measurement, you can tell by the scattering that something is there. And so before you would go on and try to do a really expensive measurement, you might as well first know that something is there. So what are we going to do? It's called LIDAR. So you might already know about LIDAR, but LIDAR is the same thing as radar. And I think all of us, I don't think it's just an American phenomenon where we all tried not to get caught by a radar trap, but that's usually why we all get to know about radar. Yeah. Okay, it's obviously a European thing too. Okay, so, but radar was actually developed during the World Wars, and it was really to see, ships, planes, whatever, okay? But ships and planes are, at least a meter, if not multiple meters big. And so the wavelength just has to be meters or multiple meters. And so that's part of the electromagnetic spectrum is radio. And so this is radio detection and ranging. I think that's what radar stands for, okay? But now we have LIDAR, which is the very same thing as radar, except instead of radio waves, we have light waves, detection and ranging. And so how does radar work? Well, okay, so I guess this is a plane. A plane is sending out its radio wave, and it's looking for something. This is obviously benign things. It's looking for a tree, and it's looking for a house. And so a pulse can come down, it can hit something, and then it can scatter straight back. And you watch the time it takes to go down, the time it takes to go back. All electromagnetic waves, it's not just light, all electromagnetic waves travel the speed of light. And so how long it takes to get down and get back tells you how far it is in this direction. And then you either imaging this or you're scanning it this way to tell you where the object is in the other two dimensions. So that's how you know something is there. But now we have light, and you can even use ultraviolet light, which is then just 1/4 of a micron. And now you can do the same thing, but look for objects that are that small, okay? And so this LiDAR will use, in this one, it's going to use a green laser. Well, it says it's using both. I don't know. You're going to have a steering mirror. You're going to scan your laser beam across the sky. Again, you're going to measure it with your telescope coming back, scattered. So, you don't see anything coming back when you scatter beyond here. For this picture, you see the most when you go right through the center, and you see nothing here. Again, you would get this kind of pulse because the earliest you would see something coming back is from this one. Okay, well, the furthest one's not very far away. Let's say there's one here, it would come back. And so that's how you get a pulse of light. So again, the time tells you that dimension, and where you're scanning tells you the other two dimensions. And that's all it is. It's the same thing as radar, but now the wavelength of our light is small, so we can look for smaller things. So mostly I want to show you this one. Again, this is my friends from INO, because I'm showing you that they put numbers to it. That's really all you really have to get out of this slide, is that they've put numbers to it. But it does show you that it's quite a small thing unless you look at this picture. So this is the LiDAR camera, but this is all the electronics that goes with it. It is ultraviolet so that they can see smaller objects. And this is an example where something is actually leaking. Okay, so it is the Trans-Canada natural gas compressor. And we do hope that industries we are hoping that all industries shouldn't want to lose their gas, right? That's just a waste for them. So they should want us all to come and measure if they have leaks. And so this is one that's looking for these leaks using this. You'll see also it says spectroscopic, but for right now, let's just concentrate on the LiDAR. So it can be small. They can find out that something's there. It's a relatively inexpensive thing. And once something's there, you can bring more to the story. Because you will need probably more to the story unless you know what's going to be leaking out and you're just looking for the leak. All right, so now the question is, why are the clouds white and why is a glass of milk white? And I apologize for my picture of my glass of milk. I don't know if it's because my dining room light fixture was yellow or the brown table made it. But anyways, we've all seen milk and we know it's white, right? So that's the question. Why is the cloud white and why is milk white? And do we all know the answer? The answer is me scattering, okay? In both cases, the answer, I don't know, is that next? Oh yeah, there we go. But it's made out of totally different things. Clouds are water droplets in otherwise uniform air. And milk is milk solids in otherwise uniform water, okay? So the water in the milk is not the scatterer, it's the milk solids. And in the clouds, it's the water that's the scatterer inside air, okay? And yet both give you scattering and me scattering. And if you shine white, not yellow light, but if you shine white light on it, it would then scatter white back at you, okay? So it tells you something's there, but it doesn't tell you what the something is. So the something, the way we do it is spectroscopy. This is showing, so this is for my friends from NRC. This is the National Research Council of Canada. And so they're showing from 2 microns to 5 microns. Different people have different definitions of what makes the molecular fingerprint, but somewhere between 2 and 20 microns is the molecular fingerprint. Every molecule vibrates with a signature that's unique to its molecule, okay? Just like we each have a unique fingerprint, every molecule, because they all have different masses, they all vibrate at slightly different frequencies. And what you're seeing here are the quantized frequencies that they will vibrate or rotate at, okay? And so these are now well known. So here's methane. I should know what that one is. I don't. Here's water. I know water. And CO2 and carbon monoxide. And sulfur oxide. Okay, I'm not a chemist. Whole hydrogen fluoride. All right. So if you were trying to see water versus, I'm going to go with hydrogen sulfide, but there may be a different name for that. That would be harder to do, but you could just look at this spectrum and make it more refined and see these various lines. All right? But let's look at this CO2. Right now, you'd want to spread that out, but you see that it's sort of sitting all by itself, so you can see it, and carbon monoxide is quite easy to see here. And so we have this tool, but it can take a bit more money or a bit more size. Doesn't have to, but let me first explain. We do have something called a spectrometer, so we use usually more than just a prism to separate the colors. We usually use something called a grating, which I also use for the compression for the CPA. But a standard old-fashioned spectrometer, let's say you were using sun, you would put a slit there. If the slit gets all the way down to wavelength dimensions, this would act like a point source of light. It would come out into a semisphere. If you put a focusing mirror here, you would collimate the beam. When it acts like a mirror, it goes off with the laws of reflection. But the grating actually lets you add a little bit more phase, and so the first order is each step in the grating actually has an angle such that the light from the one notch to the next notch will be delayed exactly one wavelength of that color. Okay? So again, if it's a peak and together and you just bring it one over, it would still be a peak again, and so it adds constructively. Okay? And that's the first order. Now, the angle that would work out is also then really dependent on the wavelength, and much more so than a prism. So this is why we could really pull the colors apart. We would pull them apart. We would then use another spherical mirror. And so each of them, each separate color, though, because it's coming at a different angle, focuses down. So it's an image of this slit, but the image goes at different positions, and you put your camera there, or you could put another slit there and rotate the mirror. So this can be a large object. Doesn't have to be, but I've been at places like NIST in the United States, NRC in Canada, and they can fill a room the size of this room, okay? And I'm sure there's even larger ones. All right, so doing spectroscopy is nothing new. This has been going on quite some time. So this is from NASA? Doesn't matter where it's from. No, oh, NOAA. Okay. So this is a telescope in Hawaii that has been searching for CO2 in the atmosphere. And so they've measured it. So in 1960, we had 322 parts per million, and it just keeps going on up. And at 2020, we were at not quite 420 parts per million. Now, some of you, although you're probably all very educated, so probably none of you, but anyway, just in case, you might be thinking to yourself, well, what's so big about that? It's like a 30% change. Do we really care about a 30% change? How different can that make? All right, so this is not the only way that you can study how much CO2 is in the air, but this is how you measure it currently. But a different way is you can go to Antarctica, where they have ice that's been there for hundreds of thousands of years, and dig down into a core and bring the core up and then measure the different layers of that ice core and determine that the CO2 levels have just been doing this for hundreds of thousands of years. So this is what you will hear a lot of people say, don't tell me about climate change, don't tell me about CO2 changing. It constantly changes. The Earth does that on itself. And the Earth does do this on itself, okay? And so in an ice age, there's no greenery, and so there's nothing to eat the CO2. And so then, of course, it starts to heat up because there's nothing eating the CO2, and then it gets so hot that there's so much greenery, so much algae, and I can tell you I have a cottage on one of the Great Lakes in Canada, and we're having an algae problem now in our Great Lakes, which have never been known to be hot lakes, but I'm telling you, we're starting to get to be a problem. But this is how the Earth looks after itself. There's an ice age, it covers all, there's no greenery, the CO2 rises, it makes the greenery, it takes the CO2, and off we go again. And so you can see that it goes up and down, but really the time span is nothing at all like we're seeing here, okay? This is humans. It can't be anything but humans. And obviously, it's gone from roughly 200, and the highest that they think they've ever seen was around 300 until humans just kept spewing stuff into the atmosphere. So this is why so many climate scientists are worried and wanting to measure the greenhouse gases, CO2 being one. Now then, the other question is, why do we think CO2 has anything to do with the temperature? And I'm going to show this one mostly because one of the other things I'm doing in public policy is trying to get a network off the ground that we call trusted research undertaken in science and technology. And I had the opportunity to see a group of people, including Dr. Fauci, but also this person here, Michael Mann, talk at the National Academy of Sciences a couple of years ago about the death threats they have received for doing science. And so after that, I went back and read this paper that Michael Mann and his two colleagues did. And what it shows is that here's been the temperature over 1,000 years, and now it's doing this. And this only went to 1999, and of course, now we're up to here. And so you can see that it follows much like the CO2, which is why they're linked together. Okay? But I still thought, what did he say in that paper that got people so mad that they would want to kill him, right? Did he actually try to put some politics into this science paper? No. This science paper is just the fact that since the mid-1800s, we've had thermometers around the world, so we know how hot the world is. Since, so the error bars you can see are very small at the end. But before that, we didn't have thermometers around the world. And so he used 3 techniques, and I don't remember all of them, but one of them was tree rings. And so the paper is about how the tree rings tell you what the temperature is, the other 2 things, how that tells you what the temperature is, what the uncertainty is in each of those 3. Then he goes on to talk about the statistics he used to put all the different measurements together so that he could come up with these error bars, okay? That's all the paper is. The paper is, this is how I've determined, or we've determined, what the temperature is over the last 1,000 years, and this is to the error bars that we can do it, and that's the whole paper. And the man got death threats. I mean, it's just mind-boggling to me. So I'm just going to say we have to stop that, okay? So, but it also is the one that showed, he called it the hockey stick, because he and I got an honorary doctorate from my old school, McMaster, so for some reason, because it was called the hockey stick, and my school gave him an honorary doctorate, I thought he had to be Canadian, but he's not Canadian. Just a weird thing. Okay. So it's called a hockey stick because if you know hockey, then this is long and this is short, and it looks like a lying down hockey stick. Anyway, we should have listened to him in 1999 and really done something because, as I said, we're up here now. All right, so back to what are we trying to do? So it's nice that there's places like Hawaii that have observatories, and I understand that here in your applied physics, we're going to do these climate measurements, and that's great. But if we really are going to have a lot of measurements, we're going to have to find cheaper, smaller ways so that we can make many, many more measurements. We can afford to do it, and they can, sit on our Earth. And so instead of using a big spectrometer, we now can have the opposite kind of laser than the one I do. I talked about mode lock lasers and the fact that we wanted as broad a gain spectrum as we could to have as many laser modes lasing at once and all phased together. Now, the other group of scientists are the ones that want to do spectroscopy. And so they work very hard to make sure only one mode gets to laze. And you remember, I called it infinitesimally small, but of course, it's not really. But it can be very small. It can be very precise. And then, so that's what it means to be single mode. And it's mid-infrared, because that's where the fingerprint is. But it's also wavelength tunable. And so this is also the National Research Council, where Canada has its standards. And so it could take it, and it could know exactly when it's operating like this, exactly what wavelength, and then they can tune either temperature or pressure to change that one wavelength. And so instead of using a spectrometer, you just have this tiny diode laser that scans across very accurately what the wavelength is, and you look, is the light coming back absorbed or not absorbed? Absorbed or not absorbed? And you just have to go through a few lines if you know you're looking for something specific like methane, because I showed you it has a very definite spectrum that only methane would have. And so now you can have this very tiny laser, don't need a spectrometer, just a detector, and measure how much of the light comes back depending on the wavelength. So it's quite small, so it can sit on a tiny drone. It can be used just to watch what's happening over some greenery, so you can watch the methane on a farm. And they're also very happy that it actually it wasn't just that it qualified, it actually flew on a Mars mission because they want to know if there's methane on Mars. And somebody tried to tell me why, but I've already forgotten why we need to know if there's methane on Mars. But somebody wants to know if there's methane on Mars. So this is a way to do it. And so if it's small enough to go all the way to Mars, it's small enough to be used here on Earth. So this is something we can do. So that gets us to what is the GEMM initiative. The GEMM initiative is not about doing one kind of science. It is really just about saying that if we are going to have all these measurements, we need to come together. Because people like me, and I do work on mid-infrared generation lasers, I'm just interested really in making the laser work a different way, a new way. And I'm sure, no, I should be careful because I'm being taped, but you do write that it could be used for ABC. In your research grants, you're going to say it's going to be a useful thing. But I will tell you, most of us that do the technology are not going to be the ones who go out and do the A, B, or C. We hope that somebody else wants to take our technology to do A, B, or C. But this is what we want to do, is build our technology. And so then, but there's other people that want to go out into the environment and take measurements, and they can really only look what's available commercially, and it'll be probably more expensive and not do exactly what they want. And so what we really want to do is bring together these groups of environmental scientists who tell us what they would like to do but still can't, and then see, do we have a sensor? And I can tell you at the first meeting at Waterloo, where we tried to get this off the ground, and we did this, one of the sensor people said, oh, I've got this great new, very small sensor. I can look for fluorine in the Great Lakes. Great. The environmental person said, well, that's nice. But what we really, really need is, can we determine chromium-3 from chromium-6? Because one of those is toxic and one of them is not. And they want to know, I don't know. They just wanted to know, at least if one of them, maybe they wanted to know both, but just didn't care about the one. Anyways, they said, can you make it work for chromium? Well, then it took me another couple of years before I had the time to get back to thinking, let's get a Waterloo GEMM Center going. And when we tried again, the same sensor person came back to the meeting. I said, did you ever do the chromium? And he said, yeah, I've already published it. I said, did you get back to that environmental scientist person? Because I forgot who suggested it. So, that's hopefully when we really get GEMM going, we'll keep people talking. And so that he finally did the one he wants, but he's maybe not told the environmental scientist. But that's really the goal, is can we get together? Can we change what the sensor people try? Because there really is a use for it. And can we get it to the environmental scientists? We have another example where somebody at Waterloo showed that their sensor worked, put it on the shelf, because that's what we technology people do. They did all they could with that. They've moved on to their new technology. And that's a shame, because if it can be useful by somebody, it should be out there being used. So that's why we want to bring the technology development people together with the climate people. We want industry at the table, not only the polluters. We want the polluters at the table to say, we don't want to pollute. They all say it. So, and we have to believe that. And they don't want to waste their materials going up into the sky. So we want them, but we also want, once the technology has been developed in research institutions, we want it moved into industry so it becomes available. We have to have international standards at the table because numbers do matter, okay? And so we really need to know that what numbers we say are actually true. And as I said, we do want government people here. We want them to know what the latest science is. We should be hearing also what they would like us to be looking at in order for, whatever government policy they think they're changing. We need to know if they are changing a government policy that has to do with the environment. We should be there to measure before, have them change it, measure after, to really see, did that government policy make the change they thought it was going to make, and were there any other effects that maybe they weren't thinking about? And so it's a two-way street. We want to feed them all our information, but we also want to hear what they're thinking about doing. Have I missed anybody? No. So that's what a GEMM's about. So here's an example. And early on, we got this group to be part of GEMM. But some years ago, Canada instituted this thing where we offered really big research dollars to try to have the reverse brain drain and bring people into Canada and offer them big research dollars. And I will tell the University of Laval, which is in Quebec City, I think was very smart and made some top-down decisions. So Laval has always been, since I've been around, It's a 400-year-old university, so probably not always. But OK, so long as I can remember, they have been Canada's pretty much leading optics university. OK, I didn't go because I can't speak French, but otherwise I might have gone there. And so it's a very good optics school. What I didn't know is that it's also very well known for Arctic biology. So when the university heard about these CERC programs, they said, OK, let's actually take our two strengths, and we can attract people because we are good in these two fields, but let's make both fields even stronger. So we'll make sure we get a CERC in Arctic biology and a CERC in optics, and we'll get the two groups to work together. Okay? And they formed this Sentinel Nord. They also are working with France at CNRS. So I'd like to show this picture, and I'll explain the picture because it's not necessarily obvious, because it's a great example of what we're trying to do. So Laval just did it on their own. They said, you guys work together, and you can help both groups to improve. So what we're seeing here is the Arctic biology problem of studying the spring bloom of the phytoplankton in the Arctic as the Arctic is melting. They just want to know how is this affecting the phytoplankton bloom. And so here's the phytoplankton, which I guess comes from bacteria, which I'm thinking comes from algae. I think this is the food thing. And it goes down to something called zooplankton. I don't really know what sinking particles mean other than they're particles that sink, so I don't know why that's something. And then onto the fish, I get fish. And then there's something called benthic fauna, which I think is just the plants down here. OK, so this is the biosphere that happens to be in the ocean, but it's being affected by also the heat in the air. So how do we understand this? This is one spot on the globe. It is the Green Edge Ice Camp. So a person can be there, a seal, I think that's a seal. A seal can be there, I think that's a sled. Or a polar bear could be there. Now, luckily, there's a hut there at this camp, so I guess if the polar bear shows up, he gets in there. But what we're talking about is these aren't all there. It's one spot on the Earth. And in the wintertime, it's got 1.2 meters of ice to stand on. Okay? You can see over here is July. There's no ice at all. And by mid-May, the holes are starting to form in the ice. Okay? And when the holes form in the ice, that's when the algae can start growing. And then it keeps on growing until in the summer when all of this is happening. So the point is, this is what the Arctic biologists want to study. And look how many, just on one spot on the globe, to study one thing. All of these measurements need to be made so that you can fully understand what's going on. The ones with circles are the photonics ones. So we're not saying we're 100% of the solution, but you can see we're a big part of the solution. Okay? And so you'd see that it's helped the optical technology people have a whole lot of new projects, and it's helped the Arctic biology people because they have many more measurements, so they really, really can understand this phenomena and how the climate is changing it. And so that's the goal, is how many times can we bring the right people together to solve a problem. Now, along with climate modeling, of course, we also have to accept that we are going to have to just adapt ourselves to it. And so one of the other projects in the CERC that came in optics is an optical fiber, special fiber person. That's not probably the right way to say it, but he makes special fibers. Okay. And so, as I said, the temperature is changing the most in the Arctic. And the Arctic used to be permafrost. Okay. Also, I will tell you, in our north, there's many regions in Canada's north that can only drive in the winter on the ice roads. Okay? There's just so much water around, they can't get out. Everything is flown in and flown out most of the time. And so the tarmacs for these airplanes, though, are on the permafrost. And unfortunately, with global warming, the permafrost is no longer permanent. And so they're buckling, and the roads are buckling. And so this project is all about what are we going to do and how can we make roads now that are not on permanent permafrost. And so they put these specialty fibers and they lay them in the airstrips and they lay them on the roads. And then when you change the pressure or change the temperature, it affects actually the polarization and the transmission through. And you can watch without even being there, because then you could send the signal back down to Laval in Quebec, and they can see what's happening with these roads buckling. Okay, so now to the GEMM initiative, and the fact that along with wanting to get each node having these groups of people work together, we want the nodes to also be networked so that we can learn from each other. And so this was one of the early ones. I don't actually know what Beacon stands for, but it's Professor Cohen of University of Berkeley. And he has these, what he calls low-cost, I've got low in brackets here, detectors. They're 10,000 US dollars. So it all depends on what you call low cost. So they're there, but they measure a lot of different things. So these are the particles, 2.5 micron size, 10 micron, and then the various gases. And he's got them on a 2-kilometer grid all over the Bay Area, all right? He certainly did take interesting measurements during COVID when he saw how much less signal there was when nobody was standing still on those bridges waiting for their turn to go across a bridge, okay? So it's on a 2 grid, but then also we are now doing it in Glasgow, Scotland, okay? It's also on a 2-kilometer grid. And in Glasgow, the detectors are sitting on schools, and so I think the idea is to get the schools involved in understanding these measurements and taking these measurements so that it is citizen science and that everybody can get involved. Now, I remember when I was at a meeting in Glasgow, somebody saying, and the public policy people were at the meeting, I thought they had said that having seen these measurements done at a school, they had been convinced to make public policy that nobody gets to drive their kid to school anymore, which I think would be good policy. But anyway, I asked before I gave this talk at Starmus, I said, is that true? And they went, no, that never happened. So here I'm putting it on tape. Sorry, cut that part out. Okay. But nevertheless, I think the school students, the teachers, and the parents all get to see what happens when the school, when kids are driven to school and they all show up there and how much the pollution rises during the start and ending of school. So it's on a 2-kilometer. But the other thing about them using the same detectors, but they also are using the same computer programs. And this is just showing you that from the stuff that they detect at this one, they can go back and find where it comes from. Now, they can't do that if they just had one detector. It is this because these detectors are on this 1 or 2-kilometer grid, and they have the weather report so they know where the wind is going, and they put all of that into these programs. But between the two schools doing it and looking at each other's data, they are refining this work so that it's becoming more accurate, and they can tell where the pollution is coming from to each of these sensors. So that's really one of the major goals. So where are we in getting this whole network off the ground? It has been since 2015 is when we started with the idea, but everything's taken a bit long. So this was one of the first ones, and then Strathclyde. I will tell you that Japan has just gone from gray, which means that they've been thinking about it to actually doing it. And my colleague sent me some slides to show you, but I couldn't open them up. I've already said today computers aren't really my thing. Anyway, but just know that they are now starting to do air monitoring there. And Waterloo just started ours this year. The Mexican Photonics Cluster started theirs this year. And so little by little, we're getting more and more of these GEMM centers. This one is one, it was interesting. I gave a version of this talk at the National Academy of Sciences, and a mathematician was in the audience, and she said, oh, I've got a friend who's a biologist working in Madagascar. They would love to have something like this, okay? But again, Optic and AGU help us network, but there's no money for the actual projects. And as I said, a $10,000 thing is kind of cheap, I guess, for a Berkeley professor, but for scientists in Madagascar, that's not cheap. And so, and again, just one isn't necessarily enough. You need a few of them. And so we haven't found the funding source yet. So, anybody listening up there on tape or wherever, you may want to help the Madagascar group. So that's why that one's a gray one. But that's all I can say. So and every one of them gets to do what they want. So some are water experts, and we have at Waterloo, we have a very well-known water institute, and so we are hoping to also get into the water monitoring and not just air monitoring at Waterloo. And so let me just tell you just ever so slightly what we're trying to just get off the ground now in Waterloo. One of them, totally separate from optics, My Dean of Science did this when he was at Windsor, which is south of Waterloo, but still in Canada, south of Detroit, actually, though. Is that just to get it into all the schools, he did it with grade 8 students in Windsor, and it's just really small vials, and they collect the water. And they just have to say what their postal code is, and is it near the house, is it under a tree, is it out in the open? They just say something like that. And every day they record how much rain went into this vial, and then they record it. And I have to say what I was even more impressed with is that he worked with one whole school district and got the whole grade 8 curriculum to put this into the whole. So they added some novel about science into the English program. They talked about the geography of rain. They talked about the math to do a little bit of data, statistics about the rainfall everywhere in science. I guess they actually did talk about the environmental science. And they got it into the entire grade 8 curriculum so that the students were really thinking about this. And so we're hoping to do this as a combination part of the Trust Network to see, does citizen science help bring trust, and then also from an environmental point of view. But we have bought one of those $10,000 detectors. We've got a couple of different types on loan from another network in Toronto, and then we've got some smaller ones that we're hoping then, can we use those in conjunction to see, if they're not as well calibrated as the expensive ones, can we still understand what's going on? And so these are the few things that we're doing. And on top of that, I'll just add that we also have a very strong School of Public Health. And so a lot of this is a public health issue. And one of the things that came up when I was at a different meeting was somebody who was talking about medical implications of so much CO2 in the air, is that he pointed out that for the entire time that humans have been on this earth, remember the picture, we have never breathed this level of CO2. And so from an evolution point of view, are humans even meant to breathe this level of CO2 all the time? And what is that doing to our bodies right now when they were never meant to have that level of CO2 being breathed into our bodies? And so there are a lot of things at play that we have to think about, not just how we're all warming up, but what it's doing to our health as of the human race. And so that's it. Thank you very much.